Let's prepare on strain energy method. So today we are going to see about the strain energy method. So among the various method of the force and displacement method, this is one of the method, okay. So here there is a direct formula to find the strain energy. So here it goes like this, that is U is equal to, use the strain energy which is equal to sigma square by 2e into volume. Okay, so volume, when you multiply it with this sigma square by 2e, so sigma we know that it is load by area, so the formula is p square L by 2ae. Okay, so this is due to axial force only, so I have given here, no, this is axial force only. This is a straight formula, okay, but in general they will be having these four formulas. Okay, so this is the main concept of this strain energy method. So always they will be taking a derivation of 0 to L and the axial force square. Okay, so the force square by 2ae, so that is only, it is derived like this. Okay, when you apply 0 to L, you will get this formula. Okay, and the next formula is when the shear force is there, you will be using the same thing but with shear force square by 2g into as. So here we know this E is the Young's modulus of elasticity here, and here G is the rigidity modulus, and as means it is the surface area, because in shear force, where the shear force is hitting, no, so at that place, in there alone we will be taking the surface area. Okay, not the whole area. And the next thing is due to the torsion, it is T square by 2gj. So here G is the rigidity modulus and J is the polar moment of inertia. Okay, and then the last one is due to the bending moment, it is m square, that is moment square divided by 2ei. So here I is the moment of inertia. So the summation of these four, u1, u2, u3 and u4, so this only will give you the total strain energy of any structure. So if you see here means I have written like this, and then the strain energy due to the axial and shear force, no, so these will be very less, so we can neglect it while calculating the problems. Okay, so we'll see an example so that you'll be clear with the concept, but most probably they won't be asking this in the exams because it takes time, but in GATE exams and IES exams they may ask those questions. Okay, but it is always better to know the concept, because with the concept they may ask any questions. Okay, so let us see just one example in this chapter so that we'll be clear with the concept. So here a question is given, a structure is given, and the question is to find the strain energy of this structure. Okay, so here this is the structure given. So if you see the structure means here it is a rigid support, it's a pinned support, and here it's a roller support. So two reactions will be there. Okay, so before going into this, you want to analyze the members, then only we can know that what force is actually acting in that member, like axial force or shear force or something. If we know that means only we can go for the formula to be used. Okay, so here two forces are like this. So as we apply the zero force member concept, no, so when you do that, this force will be surely taken by this. Okay, and here this member will be automatically zero then. Okay, and here a force P is there, no, so in the top, so obviously this member also will have a force here. Okay, so when there is a horizontal and vertical force in a joint, automatically the inclined member also will have a force there. So just I have the arrows and all, I have just drawing simply only, it's not the correct one. So there is three members and the remaining one, that is A, B, no, so it will be also zero only, because here only one force is there which is actually transferring to the incline, because incline force already has, and it is zero in the horizontal, so it should be zero in the vertical also. Okay, so in this structure here we have two zero members and other or non-zero members. So with this concept we can go into the strain energy method. Okay, so here these and this are zero. Okay, so here a force acts at A and at D, so that is a force which is equal to P here, because here comes P, no, so here also P, but here it is 0, so we can take this also as 0. Okay, and then this force P is given and the member force is taken as P here, and this is in this direction. Okay, so this is all by the force direction only. I have plotted all the directions here. So now we don't know the dimension for AC and also the force for AC, so that alone I have calculated separately here. So to find the distance of AC, just using the Pythagoras theorem, root of L square plus L square, because here L is the dimension given, so it is root 2 into L. Okay, And then I am taking just the horizontal equation. So at the point C, if you take means you will be getting the same direction, keep the same direction. Okay, so this is FBC and this is FAC. Okay, so if you take FBC, that will be equal to, in the opposite direction, FAC into cos 45 degree, because here theta is here, no, so it will be L and L in both the sides, so it will be 45 degree only. So it is BC is equal to FAC into cos 45. So cos 45 is 1 by root 2, so you will be getting 1 by root 2 of that value P. Okay, so this will be the answer here. It's positive only, and you can take it as tension itself. Just neglect this. Okay, if you take in the reverse direction means you'll be getting this answer as negative like that. Okay, so any direction you can take, that is not a problem here, because in the formula we know that we are going to square the root only. Sorry, square the load only. It is P square, no, in our formula. So obviously it will be positive only. So just neglect that and all. So we can just keep it as root 2P as the force for this member AC. Okay, so just draw a tabular column like this. First I have written the members and then the force and then the length, so that you can apply the formula. So we know the formula is P square L by 2AE for the axial force. Okay, so only axial force is applied in this structure. There is no moment, there is no torsion, and there is no shear force also. Okay, so we can directly go for this formula alone. Okay, so here 2AE will be constant in all the cases. Only P, and that is the load, and the length will be varying. Length also in only one member it is going to be varied. Okay, so let us see the members. So the first member I am taking is this AB. Okay, so AB, here the force is 0 because it is a 0 force member that we have already seen here, and the length is L, so U also will be 0 because P square L by 2A is 0. And the member BC, the load is P and the length is L, so P square L by 2AE. And the next member CD, also it is P square L by 2AE. And AD member, it is a 0 force member, so strain energy also it is 0. In the next case, this force is positive. So here root 2P and the length is root 2L. Okay, so it is P root 2 square and then root 2L by 2AE. So you will be getting 2 root 2 P square L by 2AE. So 2 and 2 will get cancelled. So root 2 P square L by 2AE. Okay, so now we are going to add this one and this one to get the total strain energy of this whole structure. So in that I have taken P square L by AE as a common outside. So in the bracket you will be getting 1 by 2 plus 1 by 2 plus root 2. So you'll be getting 1 plus root 2. So that is the answer for this question. So this is all about the strain energy. So just make sure of the concept, that is enough here, and the formulas, that 4 formulas we saw, no? So that is important here. Thank you, and keep watching for the next lecture on Castigliano's theorem.